Okay, once again, I welcome you all for my video lecture, and the topic is the Semiconductor Physics Part 2, and myself, C. Ashok Kumar, a professor, Department of EEE. And the overview goes on like this. First, I will be discussing about extrinsic semiconductor. In the extrinsic semiconductor, two types will be there. One is called as N-type semiconductor, second one is called as a P-type semiconductor. So, why you go for extrinsic semiconductors? Already explained in the last session. The conductivity that happens with the intrinsic semiconductors, which are purest semiconductors, is very, very less. Why? Because the count of free electrons and holes is very, very less. So that's why here, whatever the conductivity that happens with the intrinsic semiconductors is very, very less for electronic applications. So that's why here a need is there for us to improve the conductivity, to increase the conductivity of the semiconductors. So that's why we went for this extrinsic semiconductors, where we will be doping the impurity atoms into the crystal lattice to increase the number of carriers. Okay. So as I already said, the total conduction in the intrinsic semiconductor is by two carriers. One is, this is a valence band and this is a conduction band. So one is, I need to increase number of holes here so that I can improve the hole moment here, or otherwise you can improve the number of free electrons that are jumped from valence band into the conduction band. Okay. So one is, I need to increase the number of free electrons in the conduction band, that is one way, and other one is, I need to increase the number of holes in the valence band. Okay. So this will happen when you dope the impurity atoms into the silicon system. Okay. So that we can increase the number of electrons or number of holes. First, I want to increase the number of free electrons in the conduction band. Option 1. Okay. I need to dope an impurity atom in such a manner. I need to increase the number of free electrons in the conduction band. Okay. I need to dope an impurity into the silicon system such that I need to increase the number of free electrons in the conduction band. Other option is, I need to dope an impurity into the system such that I need to increase the number of holes in the valence band. Okay. Let us discuss about the option 1, where I am doping an impurity atom into the system, by which I am increasing the number of free electrons in the conduction band. Okay. So here, this is a periodic table, as you can see here. So here, as you can see, this 4A, this belongs to the semiconductor, silicon, germanium, like that. Okay. So here, observe the group 5 elements here, group 5A. So one is nitrogen, phosphorus, arsenic, antimony, and bismuth. So group 5A means, if you observe this group 5A, they contain 5 valence electrons. As you can see here, they have 5 valence electrons in the valence shell. Okay. And if you observe the third A group, which contains only 3 electrons in the valence shell, that will be discussed later. Our discussion is about this one. I am taking an impurity atom. I am taking an atom from group 5A. So I may take nitrogen or phosphorus or arsenic or antimony or bismuth, anything. Why? Because if you observe the number of valence electrons in this group 5A, the number of valence electrons are 5 in number, as I said. So here I am doping an impurity atom from group 5A. That is, I have taken the phosphorus atom, right? Phosphorus atom. Phosphorus atom contains 5 valence electrons. So as you can see here, I am doping one phosphorus atom into the silicon crystal. Okay. So the doping concentration will be 3 types. One is called as lightly doped. Second one is called as moderately doped. Third one is called as heavily doped. So this, what is lightly doped, moderately doped, heavily doped means? Okay. So 1 in 10 to the power of 3. That means 1 phosphorus atom in 10 to the power of 3 silicon atoms, that is called as a heavily doping. Okay. So 1 in 10 to the power of 6, it is called as a moderately doping. That means 1 phosphorus atom in 10 to the power of 6 silicon atoms. And here lightly doped means 1 in 10 to the power of 9. That means 1 phosphorus atom in 10 to the power of 9 silicon atoms. This is about the doping. Okay. So here I am doping a phosphorus atom into the silicon system or a silicon crystal. So as you can see here, the as already said, the phosphorus atom contains 5 valence electrons. So the valence electron of this phosphorus atom is making a covalent bond of the neighboring silicon atom like this. And the second valence electron of phosphorus atom is making a covalent bonding with this neighboring silicon atom. And the third valence electron of phosphorus once again making a covalent bonding with this neighboring silicon atom. And the fourth valence electron of this phosphorus atom is making a covalent bonding with the silicon atom. Right, what about the fifth one? As you can see here, it is not going to make any bonding with the neighboring silicon atoms. Already all the silicon atoms are making covalent bonds with their neighboring silicon atoms or with the phosphorus atom. So this particular fifth valence electron is free. Fifth valence electron is free. That means this particular phosphorus impurity atom, it is donating an electron for the system. Losing its negative charge, it is becoming a positive ion. It is donating an electron for the silicon crystal. That means it is losing its charge and it is becoming a positive ion. Okay. So that's why here this particular impurity atom is called as a donor impurity atom, which is becoming a positively charged ion. As you can see here, donates an extra electron that can freely travel, leaves behind a positively charged nucleus, and this is called as the n-type material. Okay, whenever you are increasing the free electrons in the conduction band, the type of material is called as n-type material. Okay, as already said, this n-type material, it is represented by a positive ion. Why? Because the impurity atom, it is losing its negative charge and it is becoming a positive ion covered with the electron. In this diagram, it is shown as a minus sign like this. So the n-type material is represented like this in a shorthand notation. As you can see here, this is impurity atom, which is a positively donor impurity atom. That's why it is represented as positive ion. It is covered with electron. It is covered with electron. It is covered with electron. But along with electrons, holes also will be there. That's why here holes are also represented. A positive symbol represents the hole. Okay. So majority carriers here are electrons and minority carriers are holes. So n-type material is represented like this. So simple representation here. A positive ion covered with electron, a positive ion covered with electron, a positive ion covered with electron, a positive ion covered with electron. So similarly here, positive ion, I did not complete my covering. So this electron. So in this notation, instead of electron here, they represented minus sign. Okay. So along with this electron, holes also will be there like this somewhere. Okay. So this is about the n-type material. Positively charged ion, which is immobile. Ion means immobile. Whenever they are covered, something happens. Whenever it is uncovered with electrons, they are immobile. That will be discussed later. And as you can see here, minority carrier. Majority carrier means holes. Minority carrier means electrons. Majority carriers. Minority carriers are holes. Majority carriers are electrons. Okay. So in another way, I am taking one more group 5A atom, that is arsenic. Okay. So I doped arsenic into the silicon crystal. Okay. Where fifth electron is free here. As you can see here, whenever I am doping the impurity atom, arsenic impurity atom, as you can see, an energy level is created just beneath this EC. As you can see, EC is the lowest energy level in the conduction band. So, beneath that, one more energy level is created here. Why? Because we doped the arsenic atom into the system. So that's why here the electron needs a very less energy to move from this particular ED energy level into the conduction band. Okay. So as you can see here, one arsenic atom in 10 to the power of 6 silicon atoms. About the concentration it is mentioned. So that is about N-type semiconductor, where I am increasing the number of free electrons in the conduction band. Okay. So second option, I am going for the second option, where second option means I need to dope an impurity atom into the system in such a manner, in such that I need to increase the number of holes in the valence band. Okay. So that's why here I need to select the atom from this third A group. What are those elements? One is the boron, aluminum, gallium, indium and thallium. So if you observe the valence electrons, 3 valence electrons will be there. Okay. So as you can see here, boron, which is having 3 valence electrons, is doped into the silicon system. Okay. So first valence electron is making the covalent bonding with the neighboring silicon atom, and second valence electron is making covalent bond. And what about the third one? Third one is making the covalent bond here, whereas the silicon atom here, valence electron of silicon atom is there, but this boron don't have the fourth valence electron. It contains only 3. So that's why here vacant space is created. That is nothing but a hole. Okay. So 3 of its valence electrons are making covalent bonding with the neighboring silicon atoms. Okay. Silicon atoms related valence electrons. So also this one and this one. And here it does not contain the fourth valence electron to complete the covalent bonding with the neighboring silicon atom here, this one. So that's why here a vacancy is there, which is nothing but we will be calling technically as a hole. Okay. Whenever you are doping boron, it is creating a vacant space, that is nothing but a hole. That means it wants to accept the electron. It wants to accept an electron. Okay. So that's why here it is called as an acceptor ion. Okay. It wants to accept an electron. That's why this particular ion is represented like this, a negative ion. Whereas earlier in the N-type semiconductors, the impurity atom is donating 1 electron into the system, losing its negative charge, becoming a positive ion. But here it is donating 1 positive charge into the system. So that's why it is becoming a negatively charged ion covered with hole. Okay. Earlier in the N-type semiconductor, it is represented as a positive ion covered with electron, or like this. Whereas here it is donating 1 hole, so that's why it is becoming a negative ion covered with hole. So you can represent like this. Okay. So that's why here the shorthand notation will be like this. So a negative ion covered with a hole, negative ion covered with a hole. In addition with the majority carets, minority carets also will be there. Those are represented as the electrons. Okay. So a negatively charged ion, which is immobile, covered with a positively charged holes, okay, which is called as a majority carrier, and negatively charged electron, which is called as a minority carrier. So these about p-type material. So same thing here, we are doping the boron into the system. Okay, here as you can see, whenever you are doping the boron into the system, it is creating an energy level here just above EV. EV is the highest energy level in the valence band. As you can see here, energy level is created. Okay, by which a vacant space are created here. Why? Because whenever you are doping a boron, it creates a hole. So whenever hole is there, as you can see here, the electrons in the valence band will be jumping into that particular vacancy. Why? Because very lesser energy is needed here. Okay, thereby creating a hole here. As you can see here, whenever you are doping boron atom into the system, so what is happening? A energy level is created, which creates a holes. Whenever holes are there, the electrons from the valence band will be jumped into that particular holes for recombination. Okay, so that's why here once again a vacancy is created. That is nothing but the creation of holes. Okay, so the creation of holes means the number of holes in the valence band is increased. Okay, which the conductivity is also increased. Why? Because here the moment of holes will happen in a large manner. Why? Because so many holes are there. Okay, so this is about the p-type semiconductor. So this is about the extrinsic semiconductors. So extrinsic semiconductor means we need to increase the conductivity by which by the process of doping the impurity into the system in such a manner, either we need to increase the number of free electrons in the conduction band or by increasing the number of holes in the valence band. We want to increase the number of electrons in the conduction band. We need to select the element from group 5A whose valence electrons are 5 in number. Okay, nitrogen, phosphorus, anything we can take. So that particular extrinsic semiconductor is called as an n-type semiconductor. As you can see, phosphorus atom is doped into the system, by which a free electron is created. Okay, by this when we can increase the number of free electrons in the conduction band, and it is represented as a positive ion covered with electron, and minority carriers here are holes. So same thing here, whenever you are doping, energy level will be created where the electrons will be there, which requires a very less energy to jump into the conduction. As you can see here, the number of free electrons are increased, by which the conductivity will be increased. So second type, p-type, where we will be selecting the group 3A element here, boron or aluminum, gallium or indium or thallium. So by which a hole will be created. Okay, as you can see, hole is created. Why? Because it contains only 3 valence electrons. So here the impurity atom is becoming a negative ion, acceptor ion, which is covered with hole. So these are representation of p-type material. Majority carriers are holes and minority carriers are electrons. So this is the thing happens whenever you dope the group 3A element, boron, which is creating a discrete level. Here the holes will be there. The electrons from valence band will be moved into this particular holes, creating a vacancy that is nothing but a hole. So here the number of holes count is increased, by whose movement that the conductivity of the current happens inside the extrinsic semiconductor. So this is about extrinsic semiconductor, and I will be stopping my lecture.